Hello, welcome to L'Hôpital's rule. L'Hôpital's rule is another application of derivative. Remember, so far in applications of derivative, so far, what have we done? We have done the mean value theorem, and we have done derivative tests. Remember, the extreme value theorem really is inside the derivative tests. Next, we're going to do L'Hôpital's rule. So the mean value theorem, the big idea between the mean value theorem was that the slope of the secant is equal to the slope of the tangent as long as you have a function that is continuous on the closed and differentiable on the open. The big idea, I should have put that across here. This is, by the way, Guillaume L'Hôpital. The derivative test, the big idea from derivative test was using the first and second derivative to find out function behavior, right? Extrema, increasing, decreasing, points of inflection, concave up, concave down. Average rate of change equal to instantaneous rate of change. Again, given that you satisfy the three conditions of the mean value theorem. Derivative test using the first and second derivative, critical points, all that kind of stuff, extreme value theorem to determine function behavior. L'Hôpital's rule, the big idea behind L'Hôpital's rule is about limits, going all the way back to the beginning of limits. How to evaluate certain limits. And the kind of limits we're going to talk about are indeterminate. Limits of an indeterminate form need Guillaume. Now, when we first did limits, we got some limits that were technically indeterminate. I didn't really use that language on you because all of the examples I gave you, we got around the indeterminate form by either algebra or a trig pattern I taught you. So I want you to recall a problem like this. If I said, what is the limit as x approaches, 5, of x minus 5 over x squared minus 25. Right? Do you remember that? And you would plug in 5, and what would happen? You would get 0 over 0. But I said, well, your first shot is to plug in, your second shot is to factor and re-plug in. This is not derivatives. This is, right? This is just taking a limit. So then you could re-plug in, and the answer was 1 over 10. The limit, right? The bumping bellies, not the limit of slopes, not the tangent, not anything. This is the limit of the function. This is what we did way back in Unit 2. Then also recall that I gave you a certain pattern to memorize, right? I said it is worth, and I told you I will teach you the math to do this problem, but it is worth memorizing as long as you are in radians and you are going towards 0. If you have a ratio of sine kx over x, as long as you're going to 0, that limit is k. So I would give you something like this. I'd say sine of 5x over 5. And you would say, oh, sine 5x over x. You'd say that's 5. Right? And I mess around with it a little bit. I'd say, oh, well, how about if it was 2 sine 5x over 3x? right? So that would be 2 times 5/3. So what if the algebra doesn't work out? What if it is not this pattern? I need a way without a computer to evaluate these limits, a computer or a calculator. And that's where Guillaume comes in. And that's what we're going to learn today. So L'Hopital's rule was named after this guy named Guillaume de L'Hopital. Now, this is when he lived, and you can tell by the way he is dressed in his wig that he is wealthy, right? And he's relatively young here too, because he was a young man, and back in these times, it was prestigious, if considered prestigious, if you gathered and talked about mathematics, right, and philosophy, and they didn't even really call it so much mathematics back then, but just, well, I guess by the 1600s they did. And if you got published, right, instead of being like a TikTok influencer, right, let me get a math paper published. So Guillaume was very interested in math, and he was good at it, but he really wanted to be considered prestigious and get published, so he didn't quite have the capabilities to get that far in math. So he said, Daddy, I want a tutor. And his daddy got him a tutor, and his tutor was one of the Bernoullis, right? So even though this rule is named after Guillaume, he wasn't really the only one, although in his publication, he did give his tutor credit. So Johann Bernoulli, and some of you maybe are in physics or know of like the Bernoullis did an awful lot. They weren't quite the wealthy aristocracy class, but they were they were tutors, they were learned people, so they weren't starving or soldiers or serfs or slaves. So they were doing okay, but they did have to work, and they worked for the rich. So Bernoulli made tons and tons of contributions to math and science, most often physics. And there was actually a couple of Bernoullis. There was an uncle and then 2 brothers, and they all 3 did an awful lot. And I forget which one Johann is. I don't remember if he's one of the brothers or if he's the uncle. Regardless, this really should be called Bernoulli's rule, but hey, anytime in math or science, if some theorem or some discovery is named after a person, pretty sure that person actually, right, was not the one to discover it. They're the one that made it famous. So there's Johann. So Johann's wig, not as impressive. He doesn't have quite as much going on here, but he's still doing all right for himself. So technically, we should say this is Bernoulli's rule, right? All right, so here we go. Here is a limit I would have given you in Unit 2, right? When we first were doing limits, and I was like, well, let's draw this function, and let's see, right? I have, right, my range walkers, right? And I have a function, and whatever this looks like, right, as I approach 2 from the left, what's my range walker with my big belly doing? And if I approach 2 from the right, what's my range walker doing? And if they're bumpy, if their bellies bump, they bump at this level, and that level is the answer to this limit, right? Nothing to do with slopes of tangents, derivatives, slopes of secants, none of that. Bumping bellies, end of story. So when you try to do this, the first thing you did was plug in. And when you plugged in, you didn't just get 0 in the denominator. You got 0 divided by 0. 0 divided by 0 is indeterminate. Why is it indeterminate? Well, because if I think about one rule I learned, anything over itself is supposed to be 1. That's one rule I learned in math. So is this 1? Another rule I learned in math was you can't divide anything by 0. So is this undefined? I don't know. It's indeterminate. It depends upon how I got here. Now, don't confuse this with the function. The graph of this function is undefined at 2. You can't divide by 0. You don't get a real number as a result. Therefore, there is no graph at 2. The function is undefined at x equals 2, right? So there is no graph at x equals 2. But when you plugged in and got 0 over 0, I taught you to try algebra and see if algebra got you out of that situation. And sure enough, this was a very simple algebra 1 factoring situation. And then you replugged in. And you really were looking at this. Plugged in 2, and you got 4. And what that means is that the graph is not defined at 2, but instead of having a vertical asymptote, that canceling out situation created a hole. And the rest of the function behaves like x plus 2, except for the hole at 2, 4. But notice my range walkers, the girl walking from the left, the girl walking from the right. As the domain approaches 2 from the left and right, the range walkers are walking on the range values, and the level that they reach is 4. And so from both sides, the limit is 4. And again, that was all great as long as the algebra worked out. But what if it didn't? What if the algebra didn't work out? What if it was another function, not a rational function, that ended up having a hole? How would I get the limit? Right? So again, the key is you get an indeterminate form when you plug in. Now again, I showed you that in this case, we can evaluate the limit by factoring and canceling, and we got 4. And we got 4. But what if we couldn't? So here's where L'Hopital's rule comes in. So this you need to write down. You need to write down L'Hopital's rule. You don't have to write this stuff down, but you do need to write that down. And as you're writing that down, do not think quotient rule. You are not taking the derivative of anything. The limit of a quotient of an indeterminate form is equal to the limit of their derivatives. That's kind of the limit of the ratio of their derivatives. So the limit of a ratio of 2 functions that are indeterminate. When you plug in your number, when you plug in A, f of A is 0 and g of A is 0, meaning you have a ratio of 2 functions whose limit is indeterminate. Then and only then. So you must be indeterminate before you can ask Guillaume to come in. You cannot bring Guillaume to the table. You cannot bring him to the limit party unless you have an indeterminate form first. So you must be indeterminate. The limit of an indeterminate form is the limit of the ratio of their derivatives. And that's why this is an application of derivatives. So just a quick proof. This proof is really not hard to do. Otherwise, I wouldn't show it to you. And since this is an equal sign, I'm going to prove going from right to left. So I'm going to start with the right-hand side here. Again, remember, when you plug in A to the original functions, you get 0 for both of them, and you're making a ratio of 0 over 0. So look at what I did here. F prime This is the definition of the derivative, right? y2 minus y1 over x2 minus x1. G prime is the limit as x approaches z a of y2 minus y1 over x2 minus x1. But remember, the limit of the quotient of two limits is just the limit of the quotient, right? And what happened to the x minus a's? Do you see what happened there? I mean, just use your elementary school fraction, right? 2/3 divided by 5/7, 5/3 is the same as 2/3 times 3 over 5, and the 3's cancel out, right? So the x minus a's canceled out, and I have f minus x minus f of x minus f of a over g of x minus g of a. But look at that gold box. What does it say about f of a and g of a? Oh, snap. That's why you have to satisfy this condition first. The proof does not work if f of a does not equal 0 and g of a does not equal 0, giving you your indeterminate form up here. Because now, look what that simplifies to. Oh, snap. See how I went from the limit of the ratio of derivatives to the limit of the ratio of the original functions. Crazy. So what that means is this first problem that I gave you, right, that I would still do with algebra. I would not bring Guillaume into this situation, but it has to work, because if I say that f of x is equal to x squared minus 4, and g of x is equal to x minus 2, and a is equal to 2, then I am talking about the limit as x approaches 2 of f of x compared to g of x. I plugged in a, which in this case was 2, and I got indeterminate. If indeterminate, then I can set up the ratio of derivative 1 to derivative 2. Now you know how to take derivatives, so the derivative of x squared minus 4 is just 2x. The derivative of x minus 2 is just 1. You get 2x, re-plug in. And shocker, what do I get? 4. La 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 la. Again, I would not use L'Hopital's on that. I would do algebra, although now that you have derivatives, right, really that wasn't any big deal to do. So again, L'Hopital's rule says if you have a ratio, you're taking the limit of a ratio of two functions, and that ratio is indeterminate when you plug in a, so you get 0 over 0, then it is true that Guillaume can come to the table, he can come to the limit party, and the limit of the ratio of the original functions is equal to the limit of the ratio of the derivatives. It just says if you're looking at the ratio of how two functions behave, the ratio of how they behave is also going to be the behavior of their tangent lines at that same point, right? That's all that's saying. So here's an example. Take a moment to copy that down. The first thing you do is plug in. Always, whenever you're doing any limit problem, you plug in first. So you're plugging in 0 for x, cosine of 0 is 1, 1 minus 0 is 0, and of course 0 plus 0 squared is 0. So I get in the indeterminate form. Yep, come on in, Guillaume. So I take the derivative of the numerator and the derivative of the denominator. Derivative of 1 is nothing. The derivative of cosine is negative sine, but I already had a negative, so I get a positive. The derivative of x plus x squared is 1 plus 2x. Now re-plug in. So remember, if 0 over 0, then Guillaume, then replug in. So plug in 0, sine of 0 is 0. Uh-oh, am I going to get another indeterminate form? No, because I end up with 0 over 1. 0 over 1 is not indeterminate, right? 0 over 1 is not indeterminate, so I stop. I got 0. I didn't get 0 over 0. I got 0 over 1. If you doubt that that is the limit, plug this into your calculator, into y1, put this ratio, and look at it at 0. Look at the function behavior at 0. Right? So you can see what I've done here. Into y1, I put 1 minus cosine x. Into y2, I put x plus x squared. And into y3, I put y1 divided by y2. So I just wanted to highlight that you can do this at any time, because sometimes when you're in a hurry, and if you just typed 1 minus cosine x divided by x plus x squared, that's not going to give you the right graph, right? The calculator follows the order of operations. You have to put parentheses around your numerator and denominator in between your divide, which is why I do it like this. I turn both y1 and y2 off, and I turn on y3, and then I can look at it around 0. Now notice that if you went here, sometimes people love Guillaume so much that they get here, and they're like, I'm just going to keep going. I'm just going to L'Hopital again. And they took the derivative of sine and got cosine, and the derivative of the denominator got 2, and then they replugged in and they got a half. They didn't do any wrong math, but they didn't satisfy the conditions of the L'Hopital's rule. So if you look at the graph of 1 minus cosine x over x plus x squared, and you look at the behavior around 0, it ain't going to be a half. It is going to be 0. You cannot apply L'Hopital's rule unless when you plug in your value for A, you get the indeterminate form. Okay, very important. So let's go back to that example that that we did in Unit 2, right? The sine x over x trick. I told you to just memorize this was going to be 5. But let's pretend you'd forgot that. If you plug in 0, sine of 5 times 0 is 0. Plug in 0 for x, and I get 0. Indeterminate form. Let's go, Guillaume. Let's go. So this is equal to the derivative of x, which is 1. I already know I'm not going to have to do L'Hopital's after this, right? I'm not going to have to do L'Hopital's because I only do L'Hopital if I get 0 over 0, and right now my denominator's 1. It ain't going to be 0. Now, what is the derivative of sine of stuff? Cosine of 5x times 5. Replug in, and you get 5 times cosine of 0. Cosine of 0 is 1, so sure enough, you get 5. Math is so cool. Woohoo! I think I might love Guillaume. Don't tell Mr. Getz. But he's got to get rid of that wig. Who is it that told them back then that those wigs were attractive, right? Somebody did, because they all wore those wigs. Ooh, look at me, I'm wealthy. Look what I can buy, right? A wig with a bunch of, bunch of curls, and I look silly, but they look silly to me now from my right standpoint, because it's not normal, but for them it was normal. So who am I to judge, right? All right. Yes. Please don't, just because you know Guillaume's rule, you can't use Guillaume's rule if you don't satisfy the conditions. But sometimes I do have to use Guillaume more than once. So look at this one. Verify that it's indeterminate. Take a moment as you're copying down. Is that indeterminate? First thing you do is plug in. 1 plus 0 is 1. Square root of 1 is 1. 1 minus 1 is 0. Minus 0 over 2 is 0. Plug in, yep. 0 over 0. Bring them in. Let's go. Now, I didn't use Guillaume yet. Do you see what I did there? All I'm doing here is rewriting my radical, right? That's the only thing I did was change the radical to the power of 1/2. Now remember, you're not doing the quotient rule. You're not taking the derivative of a quotient. You are using L'Hopital's rule, which says the limit of an undeterminate form of a ratio of two fractions that result in indeterminate is the same thing as the limit of their derivatives. Yep, come on. So bring the 1/2 down, copy over the middle, subtract 1 from the exponent, multiply by the derivative of the inside, but that's just 1. And then the derivative of negative 1/2 x is just negative 1/2, but the derivative of x squared is 2x. Replug in. When I replugged in, I still got 0 over 0. Right? Because I have 1 plus 0 here, which is 1. 1 to any power, except for 0, is 1. 1 times 1/2 is 1/2. 1/2 minus 1/2 is 0, and certainly that's 0. So I have to Guillaume again. Yep, double Guillaume. Let's go. Brought the negative 1/2 down, multiplied by, got negative 1/4, copied over the middle, multiplied by the derivative of the middle. Right? It didn't matter this time because the derivative of the inside is 1, but that's going to mess all of your work up if you don't remember the chain rule. Subtract 1 from the exponent, and the derivative of negative 1/2 is 0. The derivative of 2x is just 2, so I already know that I'm not going to need Guillaume anymore because I can't possibly get 0 over 0 if my denominator is a constant. Not 0 over 0, do not Guillaume. Just replug in. So I'm putting 0 in here. 1 plus 0 is 1. 1 to this power is 1. 1 times negative 1/4 is negative 1/4. Negative 1/4 divided by 2 is the same as negative 1/4 times 1/2. And I get negative 1/8. Ta-da! So Guillaume, not Guillaume. Now there are, L'Hopital's rule was used with the indeterminate form 0 over 0, but was then expanded. There are other indeterminate forms. The second most famous, besides 0 over 0, is infinity over infinity. Again, this is indeterminate because, oh gosh darn it, I keep kicking out my cord. Because, again, I thought anything over itself was 1. But infinity is not a number, it's a description, right? Well, exponential functions get to infinity way faster than log functions. And if you have a ratio of exponents to logs, that's not going to be 1, right? Here's another indeterminate form. A product of infinity times 0. I thought anything times 0 was 0. Well, any number times 0 is 0. This is actually indeterminate. Kind of mind-blowing, isn't it? Infinity minus infinity. I thought anything minus itself was 0. Well, again, it depends upon the size of infinity. And remember, infinity is a behavior, so you're not actually infinity. 1 to any number. I thought that was going to be 1. Well, infinity is so big, it's kind of crazy. 0 to the 0 power. I thought anything to the 0 power was 1. Infinity to the 0 power. I thought anything to the 0 power was 1. OMG. These are the most common indeterminate forms. So those are the ones we are going to deal with. When you have infinity over infinity, you deal with it just like you do 0 over 0. Notice that the indeterminate form is a ratio. None of these indeterminate forms are ratios. So I have to do some calisthenics, some backflips to change them into fractions. Well, I can change any product into a fraction, right? Because multiplication, I can just change it into division of the reciprocal. I can take two things that are being subtracted and get a common denominator and make it into one fraction. Guess what it takes to turn any exponential expression into a fraction? Oh, you didn't see it coming, did you? You didn't see it coming. Ah, it's going to take logs. Now, we are not going to have to do those. We are going to deal again with the most famous. But when you take calculus for real in college, right? It is this, even though this is BC calculus, it is still high school. It is still not real. If you are interested in going on in STEM, you are going to have to do college calculus, which definitely delves into theory and does a lot harder problems than even we're doing. All right, so let's look at this one. X, now, sorry, I said we were just going to deal with the ones that either are fractions or can easily be turned into fractions. We are not going to do the log ones. All right, so look at this one. It is a product. X is going to infinity. So if you put infinity in for X, you get shockingly infinity, but you're not actually getting infinity, right? You're getting bigger and bigger and bigger numbers. Times the sign of 1 over really, really, really big numbers. But what is the sign of really, really big numbers? I'm sorry, what is 1 over really, really big numbers? Isn't that getting really, really, really close to the sign of 0? But what is the sign of 0? Sign of 0 is really, really close to something really, really close to 0, yes? So I have the indeterminate form, 0 times infinity, and I got to backflip that into a fraction. So think about elementary school. If you had 2 divided by 1/3, you were taught that division is the same thing as multiplication of the reciprocal. I need you to go the other way. Multiplication is the same thing as division of the reciprocal. So I need you to take this product, which was infinity times 0, which is indeterminate, and take one of them and make it a reciprocal, make it a ratio. And it doesn't matter which one you put on top and which one you put on bottom. In general, it's nicest if you reciprocate, right, the simpler function. And now, is this indeterminate? Well, we already decided that if you're plugging in infinity for x, 1 over infinity is 0, sine of 0 is 0, or getting, right, again, a limit means you're getting really, really close to. 1 over infinity. Oh, finally. Come on in. You've been waiting. Oh, I should do like the Zoom. Ding dong, ding dong. Guillaume's in the waiting room. I have an indeterminate form, so now I can use L'Hopital's rule and say this is equal to the limit as x approaches infinity of derivative 1 compared to derivative 2. And it would be the derivative of sine 1 over x and the derivative of 1 over x. So I'm going to erase this because I typed in all of this work. So it's a little neater and I don't run out of room. So this approaches infinity times 0, which I showed you. So I did my backflip to take infinity times 0, and I made a ratio, a convenient ratio. Again, it doesn't matter. Sine 1 over x could be on the bottom. It doesn't matter. I reaffirmed that this was the correct indeterminate because this was indeterminate, but to use L'Hopital, I need the ratio, either infinity over infinity or 0 over 0. Yep, let's go. Now, I again wanted to show you on your calculator what this answer is going to be. And I showed you the power. If I already had from the last problem, y1 divided by y2 into 3, I just have to change my y1 and my y2 and turn those equations off because I already had that in there. That's kind of nice. So I'm going to take the derivative. Whee, here he comes. So take a moment to make sure you're okay with where that came from. The derivative of sine is cosine of the stuff. Spit out the derivative of the stuff. The derivative of x to the negative 1 is negative 1 x to the negative 2. If you did not remember the chain rule, look what happens when you take the derivative of 1 over x by itself. Bye. Right? If you've forgotten the chain rule, that nice algebra wouldn't happen. So now what do? We replug in. So I have the cosine of 1 over infinity, but 1 over infinity is 0, or approaching 0. And the cosine of 0 is not indeterminate. It's 1. Woo-hoo! If you looked at the graph of this function and zoom in around 0, the graph of x times sine over 1x, or the division, sine 1 over x divided by 1 over x, either one of those, they are the same thing. That's the power of algebra. You would see that you got 1. And again, if I was trying to do this in unit 2, there's nothing I could do. There's no algebra that gets me out of, what the heck, infinity times 0. Again, you might think infinity times 0 is 0, but it ain't. Not in this situation. It's because of the behavior of sine around there, around 0. I'm sorry, towards infinity, right? It oscillates. All right, last one. Using L'Hopital with one-sided limits. So notice here I am asking you about the limit as x approaches 0 from the right. So at first I just ignore that, right? And I say, well, what am I going to get when I plug in 0 from the right? I say to myself, I'm going to use Guillaume because I have 0 over 0. So what happens when I plug in now? I get cosine x over 2x. Is this indeterminate? After Guillaume, zero over 0 means bring Guillaume. After you Guillaume, you replug in. And what do you get there? Don't you get 1 over 0? Is that indeterminate? I don't think so, right? That's not indeterminate. 1 over 0 is not 0 over 0. So what do I have? So here, this is undefined. That's not indeterminate. And if it's not indeterminate, I can't go and keep using Guillaume. So I have to think, what's going on? So instead of just plugging and chugging, I actually have to think, what's happening as I plug in numbers, right, because I'm not actually plugging in 0. I'm plugging in numbers really, really close to 0 from the right. So in reality, I'm plugging in cosine of 0.0001 over 2 times 0.0001. Right? Well, remember what cosine, do you agree that this is certainly 2.001, right? This is positive. And cosine of 0.00001, you know what cosine looks like, right? So that's positive. This is positive and really close to 1, though, right? But what's happening here? 2 times 0.0001, 2 times 0.000001. What do you think is happening there? That's swooshing off to infinity, right? 1 over, right, positive infinity. And again, if you don't believe me, just, put a couple of things of those into, put a couple into your calculator, or just put that graph into your calculator and see what's going on. How about from the left? From the left, I get 0 over 0, which means I'm going to bring Guillaume to the situation. Darn it. I got 0 over 0 from the left. Going to bring Guillaume to the situation. Took the derivative of the numerator and the denominator. Then I replugged in. I did not get, this is not Guillaume. That is not indeterminate. So I have to think what's going on. Think. This time I'm putting in numbers, really, really small negative numbers, over 2 times really negative numbers, right? Because you're plugging in 2 times negative numbers, so I'm going to get negative. But what about the numerator, right? Cosine of 0 is still up here at 1, so this is still going to be close to 1, but this is going to be negative 2 times, blah, whatever. So where's that going? Negative infinity. So what that means is this graph, whatever it looks like, has a vertical asymptote at 0. And from the right, swooshes up, and from the left, swooshes down. But I had to get to, Guillaume had to tell me I had undefined. So from Guillaume, I got undefined. And then from undefined, I had to investigate the behavior. In the previous problems, we had a whole, right? So we did have undefined, but we found out what the behavior was around there. Now, I also want to tell you a little secret about your pre-cal experience and Algebra 2 experience. Do you remember end behavior of polynomials? And we taught you a trick. And we said, if you had, for example, right? If you did this, what is the end behavior? And you said, oh, well, the numerator is not as powerful as the denominator, so that's 0. Well, let's pretend you didn't know that. If you plug in infinity, isn't this infinity over infinity, which is L'Hopital, which means you can bring Guillaume to the situation? Which is still infinity over infinity, which means you can still bring Guillaume to the situation. What happens when you plug in now? This is not indeterminate. Your numerator is 2. So this is 2 over 6 times huge, huge numbers. What does that go towards? 0. Right? So the whole reason you've got those polynomial rules, right, of remember what happens if it was the other way. If this was 3 and this was 2, you'd say, oh, there's no horizontal asymptote, but there is a slant asymptote as you go to infinity. You know what that's, you know how you're going to find that? It was really Guillaume all along. Or what if the powers were equal, right? And this was a 2 and this was a 7. That limit would be 2 over 7 because the powers were even, but it really was Guillaume that did it. Oh my gosh. You were using Guillaume and you didn't even know it. It was like behind the scenes. He was hiding behind the door. That is it for L'Hopital's rule, which is, again, another application of derivatives, because in order to do these kinds of limits, you couldn't do these kinds of limits before you knew derivatives. But now that you do, you could welcome Guillaume, invite him to the party when it is appropriate, and he will help you get the limits. All right. I will see you in our live session.